Okay, so we had seen oblique collision of a particle with a rigid surface. So we saw if a particle impacts a surface with a velocity v naught, which is at some kind of an angle theta, non-zero angle theta, with respect to the normal. And we saw that the approach velocity becomes v naught cos theta, and the tangential velocity, the tangential component, becomes v naught sine theta. And upon impact, what happens is that the direction of the approach velocity or the component normal to the surface gets reversed, whereas the component tangential to the surface remains unaffected. So if the particle had come in along this direction, this angle is theta, now it can, in general, after impact, it will have a velocity which is in this sort of direction. Okay, where this angle is, let's say, phi. Okay, so if this is the situation after impact, then we can see that in this diagram, the separation velocity is v cos phi, the normal component that is, and the tangential component is again v sin phi. So the general formula here was that coefficient of restitution being defined as the ratio of separation to approach velocity. V cos phi becomes v naught or E times v naught cos theta. And v sin phi is equal to v naught sin theta, because the tangential component of momentum is conserved. Okay, so this was the discussion in the previous class. So let's begin today with a revision question of this, and then we'll move on to the next part of collisions. So in this example, we have an inclined surface of angle of inclination 37 degrees to the horizontal. And then we drop a particle from a certain height above it. Now, what we observe is that immediately after dropping the particle, immediately after impact, the particle has a horizontal velocity. Okay. So a particle is dropped from a height of 20 meters. Take the value of g as 10 meters per second square. And after impact, its velocity is horizontal. Then of course, as it moves, its velocity changes. It goes into this kind of projectile motion. So this is just after impact. So we want to find V and find the coefficient of restitution E for the collision.
Sir, I've sent you the answer.
Yes, Darsh, your answer is correct. Akshat, you have to check. I think something about the angle you might have mixed up. So let's understand how this will work out. Yes, Laksh, your answer is correct. Very good. So if this angle here is 37 degrees, then the impact velocity, which is vertically downwards, that will also be making an angle of the same thing, 37 degrees with respect to the normal. If it impacts with a velocity v0, now we know that v0 is going to be root 2 gh. So in this case, it's going to be 20 meters per second because h was 20 meters. Okay. But more importantly, what is the angle made by this with respect to the normal? So this angle is 37 degrees. So again, you can see that the approach velocity, this is the normal component. And the tangential component, so this is the picture before impact, just before impact. Now what's happening just after impact? To visualize that. Now the question is telling us that immediately after impact, the velocity it develops is a horizontal velocity. So immediately after impact, its velocity is horizontal and like this. So you can see that with respect to the normal, this is at an angle of 53 degrees now. So this has a separation velocity which is V cos 53 degrees over. And it has a tangential component is V sin 53. Okay. Now tangential component is conserved. So that is going to give us that V sin 53 degrees is V0 sin 37. So that is what is giving us our first relation here, that what is the value of V. So you can see that okay, and as expected, V is less than V0. Okay. So you can understand that it is a it is an inelastic collision. E is less than 1. Okay. So note down this first, and then from this try to find out the coefficient of restitution if you haven't already. So Laksh and Darsh, your answers are correct for E also.
Sir,
Sir, done.
Done, sir.
Yes, very good. So, Akshat, your answer is also correct. So, for coefficient of restitution, now we can just see that this ratio. So, the separation velocity, as you can see above, is 3 by 5 v, and the approach velocity was 4 by 5 v naught. So 3 by 5 into 15 divided by 4 by 5 into 20. See, that is 9 by 16. So that is the coefficient of restitution. Okay, so hope this question is clear to all of you. Now we move on to the next part of collisions. Okay, finish writing this down.
Sir,
Yes.
sir, I had some doubts in the circular motion DPT, so can we discuss it at the end of the class?
Okay, okay. Okay, so moving on now to the last part of collisions. So we'll see oblique collisions of two particles or bodies. Okay, so supposing so when they come in contact, the collision impulse will act along the center to center line if they are spherical or round bodies like this. And as a result of that, after impact, their velocities might become like this. So conservation of momentum, here it becomes a vector relation. So this equation has to be solved by component algebra. Okay, so let's see a basic level question, how this concept is implemented.
Just a second.
Okay. Okay, so suppose we have this situation now. We have this fairly large size round object which is at rest initially. And we have another much smaller particle-like object which is moving with a velocity in this sort of a direction. It comes and hits this. Okay. Now after impact, okay, M1 is deflected by 90 degrees. Whereas M2 moves at velocity V2 at an angle theta with respect to the line of action of the velocity V0. Okay, that is. So given these are the masses. Okay. V0 has a magnitude of 4 meters per second and theta is equal to 37 degrees. You want to find the magnitudes of the final velocities V1 and V2. Okay, so just take down the data of the question and set up the diagram of what happens during impact and what happens just after impact. From that, try to apply conservation of linear momentum in component form, and we'll see how we'll come up with the equations.
So we'll take components along the line joining the centers.
Not necessarily, we can take components as is convenient. Like in this case, you can see that the velocity after impact for M1 is at 90 degrees to the velocity before impact, no? Because it's deflected by 90 degrees. So it will make sense to take those as X and Y axis, no?
Okay, yes.
And automatically our V2 will become at 37 degrees to the X axis because theta is given as 37.
Yes.
Okay. But yeah, in certain cases, especially where we have to implement the coefficient of restitution, here there is no implementation of coefficient of restitution. We'll solve the problem only by momentum conservation. So here the axis will be more convenient, like X axis along the velocity vector V0. But yeah, in certain cases where we have to apply coefficient of restitution concept, then we will take the components along the center to center line and perpendicular to that.
Okay, sir.
Okay, one more thing we can be asked to calculate here is find the collision impulse. Okay, J. That is the magnitude of the impulse that M1 applies on M2 or vice versa, M2 applies on M1. That will be same magnitude either way. Okay, so I'm just setting up the diagram. Now let's put all the information that is given. Okay, this is right. Now what happens is after impact, so immediately after impact, this is what we are observing. That this one has a velocity which is perpendicular, and this one okay with respect to the line of V naught. So obviously when they come in contact, there is a collision impulse that acts along the center to center line. Okay, so let's work this out. So now if I take this direction as my x-axis, and therefore this as my y-axis. So you can see that momentum conservation for the system here will tell me that m1 v naught is equal to m1 v1 plus m2 v2. So when I write this in component form, I have m1 v naught I cap is equal to, on the other side, m1 v1 j cap plus m2 v2 into cos theta I cap minus sin theta j cap. So I have this relation that this is my equation in component form. So as we solve it, you can see that equating the x components, we have m1 v naught on the left hand side is equal to m2 v2 cos theta. So 1 into 4 is equal to 4 into unknown v2 into cos 37. That is telling me that v2 is 5 by 4 or 1.25 meters per second. And same thing when I balance the y component, you can see left hand side y component is 0, right hand side it is m1 v1 minus m2 v2 sin theta. This is telling me that okay, so 1 into v1 is 4 into v2 into sin 37, which is 3 by 5. So this is like our second equation. This was our first equation. So from the first equation, we are getting this as 5 by 4. So from this, you can see that v1 I think will become 3. Now, in terms of impulse, you can see that the impulse acting on body 2 because of body 1 is of same magnitude as this impulse. So suppose that is J. Now, for M2, this impulse is equal to the final momentum. Okay. So the magnitude of the impulse is this much. So it is 5 Newton second. Yes, very good. In vector form, we can write it like that. So in vector form, we can see that it's having a momentum of 5 at 37 degrees. So it will be 4 I cap minus 3 J cap. So the impulse acting on 1 because of 2 will be opposite of this. So you can also check one thing here, that the impulse acting on 1 because of 2 is equal to M1 V1 minus M1 V0. If you do this vector algebra, you can see this will also work out. So here we are using the concept that impulse is equal to change in momentum. This one had an initial momentum which was 0, so it was easier. But M1's momentum is changing from M1 V0 to M1 V1.
Yes, sir.
Right, so this question is understood, I hope.
Yes, sir.
Okay. Okay, let's look at another relatively simple question where only conservation of momentum is going to be implemented.
Sir, can you show above part for a minute?
Yeah, I'll show just a moment.
Done, sir.
Okay. Okay, now let's look at this question. So this time we have two bodies of identical mass. And this one is at rest. mass of A is equal to mass of B. Okay. Now, after impact, okay, A is deflected by 30 degrees at velocity v1, and B's velocity v2 has same magnitude as v1. Okay, so and in this case, let's also find the coefficient of restitution. So we will discuss in detail about how to find coefficient of restitution. So for that, we'll have to see how to calculate the relative velocity of approach and the relative velocity of separation. But before that, work out v1 and v2, and that is going to be very simple. That is just going to come by conservation of momentum. So you should be getting this result that magnitude of V1 is equal to magnitude of V2, which will be V0 by root 3. Okay. And the angle between V1 and V2 will be 60 degrees. Okay. Now we'll calculate the coefficient of restitution also, but first let's see how we get this result. So this just comes by momentum conservation. So it's given to us in the question that the first body A, it deflects by 30 degrees. Okay. So what that means, let's understand. So that means after impact, this angle will be 30 degrees. So let's say this angle is now theta. Okay. So we know that the masses are equal. We know this is 12 meters per second, and we know that magnitude of V2 is equal to V1. This is also given. So applying conservation of momentum, we can see that this is the case here. Okay. So once again, if we take this as our x-axis and this as our y-axis, we can see that when we divide this into component equations, just a moment. Okay, so this equation is going to give us that mv0, m of course cancels off, okay, is mv1 cos 30 degrees plus mv2 cos theta. So 12 is equal to root 3 by 2 v1 plus
So
v. Yes.
I have sent you the answer for a coefficient of restitution. Can you please check?
Okay, we'll discuss it. Just a moment. Huh? Now along the y component, the initial momentum was 0. And the final is mv1 sine 30 minus mv2 sine theta. So this tells us that v2 sine theta is equal to v1 sine 30 degrees. This is our second equation. So when we implement this here, we see that we get this. Okay. And then when we substitute that here, Okay. So from this, we can also see that since theta is equal to 30 degrees, that is the angle between the two vectors v1 and v2. Right, now we'll verify the coefficient of restitution. So once again, we will interpret coefficient of restitution as the ratio of separation velocity to approach velocity. So to understand that separation to approach velocity, we have to look at the impulse picture very carefully, because the impulse acts along the center to center line. So this is the situation after impact. So if we were to compare this with the collision impulse that is acting, okay, so you can see that the collision impulse acts along the center to center line, which is at this angle theta. So this theta is equal to 30 degrees. We worked that out. Okay. So now if we compare this situation to just before impact. Okay, so just before impact, what is happening is that this is having a velocity which is at an angle of 30 degrees again with respect to that center to center line. Okay, so here you can see that the approach velocity is going to be how much? It's going to be the component of this v naught towards B center. So it is v naught cos theta. So it is 12 cos 30. So it is 6 root 3. This is our approach velocity. Okay. Now similarly in this diagram, see that this is our center to center line. Okay. So this whole angle here, this angle is 60 degrees. Okay. So what is our separation velocity? Our separation velocity is like this, that this is going directly along the center to center line at v2, but this is having a velocity v1 like this, where this is at an angle of 60 degrees. So this one's component, A's component towards B is v1 cos 60. Okay, and V is directly running away at v2. So the separation velocity will become this, become v2 minus v1 cos theta, cos 60. Okay, so v2 we had seen was 4 root 3. So was v1. So this becomes 2 root 3. So that is our separation velocity. Whereas this was our approach velocity. So from this now we can see, okay, Yes, Parv, your answer is correct. Coefficient of restitution, the ratio of these two will become 1/3. Okay. Now we will come to one very important theorem related to oblique collisions of this type. If a particle or makes a perfectly elastic oblique collision with a stationary body or particle of identical mass, then their final velocities after impact will be perpendicular. Okay. So here the necessary condition is that it's perfectly elastic and identical mass. So essentially what it's saying is that if a body moving at a velocity v0 like this comes and hits another body but obliquely, which is at rest, then after impact their final velocities will have to be perpendicular to each other if the collision is perfectly elastic. So let's understand why this is happening. So there are a couple of ways to understand that, okay, and we'll discuss all. One way is to understand by just using the more fundamental property of perfectly elastic collision, that not only E is equal to 1, but also kinetic energy is conserved. So if we implement that, you can see it's very easy to prove this. Momentum conservation gives us this equation, which tells us that the vector sum of v1 plus v2 is equal to v0. Okay, and conservation of kinetic energy gives us this, which gives us that okay. So now from equation 1 we can see and from equation 2 we can see that which implies that magnitude of the vector sum of v1 and v2 is square root of v1 mod square plus v2 mod square, which means that v1 is perpendicular to v2. So this is given as a proof question in HC Verma. Okay, whereas once you've done the proof, you should remember this as a theorem because this can be directly applied in questions. We'll discuss that also.
Sir,
Yes.
sir, so the momentum of that body which is in motion gets distributed proportional to the masses.
No, not necessarily proportional to the masses. Okay. It all depends on the angle of contact. It depends on coefficient of restitution as well as the masses. You're understanding, you know?
Yes, sir.
Okay, so let's look at an example question where we implement this theorem. Okay. Finish writing this down first.
So done.
That's it.
Okay. So now let's look at a typical question where if we utilize this theorem, then solving of the question becomes much easier. Of course, even if you don't remember this theorem, this question can be solved, but it will just take that much longer because you'll have to figure out that the final velocities are perpendicular. So anyhow, let's understand the question I'm talking about. So we have these two identical disks, let's say, on a smooth horizontal surface, like two carom coins, basically. So these are identical disks on a smooth horizontal surface where while this one is moving, with an initial velocity vector like this. So the line of that velocity vector like this. The second one is at rest. Okay. And they're identical and they're going to make a perfectly elastic collision. So that's the center of the second body. Okay. So A and B are identical disks on a smooth horizontal surface. Of mass 1 kilogram each and radius equal to, let's say, 2 millimeters or 2 centimeters each. Now B is initially at rest. And A moves at a speed of 10 centimeters per second, such that the impact parameter. Now I'll explain what is this impact parameter. So this quantity here is 2√3 centimeters. So what the impact parameter means is that this perpendicular distance this is the impact parameter. Okay. So it is the perpendicular distance of the line of action with respect to the body B's center. So that impact parameter is given to us as 2√3. Okay. So we have to find out if the collision is perfectly elastic. We have to find out the final velocities after impact. So this is a question which is of slightly higher difficulty level because the information given is quite indirect. Okay, there is some indirect information given about the angle of impact, but you have to calculate that by using the geometry, the relationship between the radii, which are equal for both of them, 2 centimeters each, and this impact parameter which is given. So when you draw the situation when they are coming in contact, and you join the center to center line and you compare that with respect to this impact parameter, that will indirectly give you the angle of impact. So that is one thing. And the other thing is you use the theorem that we've just discussed, that if the masses are identical and this type of collision is perfectly elastic, then the final velocities VA and VB must be perpendicular to each other. So if you use that theorem, you'll see that that cuts short the solution a lot, and this question can be done within a couple of minutes without much difficulty. If you don't use that theorem, also the question can be solved, but it will just become a little bit lengthier because you'll end up proving that theorem by using this question.
Sir, I have sent you the answer.
Okay, so let's see what we've come up with this over here. Yes, very good, Parv. Your answers are correct. And what about the angle of VA and VB with respect to V naught? Can you tell me?
Sir, VA would be 30 degrees.
Yes, correct. Very good.
VB would be 60.
60 degrees. Very good. That's correct. Okay, so to understand the impact, so we just do a comparison of these before impact, during impact, and after impact. Now in this only we can see that the center to center line, it is of length 2r. And when we drop this perpendicular here from the direction of V naught, we saw that the impact parameter was that quantity given to us as D. So we take this angle as theta, we can see that theta is equal to sine inverse of D by 2r here. So that is becoming sine inverse of 2 root 3 divided by 4. So that is becoming 60 degrees. So theta is 60. Okay, so that is the geometry part. Okay. Now coming back to all this, you can see that now the masses are equal and the coefficient of restitution is 1. So obviously this one's final velocity will be along this line because the impulse acting on it is along this line. So from impulse momentum theorem, understand that this will have a final velocity along this direction. Now using the theorem that E is equal to 1, which means here that V2 will be perpendicular to V1. If we just use that, we'll understand that this velocity will be at 90 degrees here. Okay. So this angle, let's say phi, will become 30 degrees. Okay. So that is using this theorem. So using this theorem now, so when we apply momentum conservation, now we can see that this equation is reducing to the fact that V0 is equal to V1 cos phi plus V2 cos theta, or V0 is equal to okay. So actually this we can say is our equation 2. This was our equation 1. And okay, so now solving from equation 2 and 3. So you can see we will get this. V1 can be replaced with root 3 V2. You can see that kinetic energy is also being conserved. Okay, people. So these are the general methods of solving oblique collisions in 2 dimensions or by using 2-dimensional component algebra. Okay, so we'll conclude today's class here today. What was the doubt you had from the DPT in circular motion? One of you had.
Sir, should we send you the sum or?
Yeah, just send me the picture of the question on WhatsApp.
Okay, sir.
Also, sir, I had sent you some doubts on WhatsApp earlier.
Okay, I will send you some. Okay, so I'll give you the general idea of how to solve this question. This is part of a longer subjective question, which was actually a previous year IIT question, but it was a subjective IIT question. So it was from way back in JEE, when JEE used to be a subjective exam. Anyway, so in this question, what is happening is you have a particle attached to a thread like this of length L, let's say, given a velocity V0 over here. And that V0 is obviously something which is such that the thread loses tension at some position like this. So the diagram is little incorrect. This angle is theta, not the angle of the projectile motion thing. I'm coming to that. So here if tension becomes 0, so now from here onwards, from here onwards, the motion will become projectile motion. Now we have to find the condition that as part of that projectile motion, the particle passes through this point where it was suspended. Okay. So first of all, we'll see here that the condition for tension to become 0 is that if it's having a velocity v, this angle is theta here. Then tension equal to 0 at this point means that mg cos theta is equal to mv square by L. So v is equal to root gl cos theta. Here we need only this equation because you have to relate theta such that this happens, the condition that this particle passes through this point. So just this equation is enough, but otherwise you can relate V0 and theta using work energy theorem. Okay, now we come to the projectile motion part. So for the projectile motion part, what is happening? This particle from this point has a velocity v, which is given by root gl cos theta at an angle theta like this. Okay. And take this as the x and y axis. So its trajectory has to be such that it passes through this center point of the circular motion. Okay. So if you look at the center point, its coordinates with respect to my xy system are what? The center has coordinates equal to, the x coordinate is L sine theta and the y coordinate is minus L sine theta. So these coordinates should satisfy the equation of trajectory. Okay. And what is the equation of trajectory? So the equation of trajectory is that y is equal to x tan theta minus half gx square upon u square cos square theta. So here we will substitute u as this quantity. Okay, and we'll substitute x and y as this. So when we substitute this, should get minus L sine theta is equal to x, which is, sorry, something wrong with the x. It should be, sorry, y should be minus L cos theta. Okay. So minus L cos theta should be equal to x, which is L sine theta into tan theta minus half g x, so that is L sine theta square upon u square, which is gl cos theta, u square cos square theta. So, okay. So this equation now you have to solve it for theta. So that will solve this question. But for example, if you want V0, for V0, now you use the value of theta, okay, in work energy theorem. So work energy theorem wise, you'll have this, that okay, so once you get theta from here, you can find the value of V. So you can put that in this equation, okay, and find the value of V0. So you'll also find at what speed the particle has to be projected from the bottommost point, or it has to be thrown horizontally from the bottommost point. So hope you understood the solution of this question.
Yes,
So it's better to go from the trajectory way rather than going for projection from an inclined in that.
Yeah, always it is better in this type of situation to go with the equation of trajectory. Because actually, first of all, it's not an inclined plane. No? The particle is a free projectile. It's just that during its trajectory, it is passing through that center point, right?
So like if we took it from inclined plane, then like we could find the range. So,
So the range should be equal to L on that inclined surface. Okay.
Ah.
But you can't use the standard formula because here theta is not the angle with respect to the horizontal. Okay. So you'll
yes.
have to be a little careful. If you're doing it by a formula based method, you have to adjust the various quantities carefully in that. Okay.
Yes, sir.
sir, I had a doubt in center of mass.
Guys, we'll pick up the question in the next lecture. Or which center are you in?
Sir, I am at TP Bhattacharya Center. Andheri.
Okay, so you are having the physical doubt sessions also, no? At the center this week.
No, sir, we have not gotten any message yet.
Okay, okay. So in the coming week, we will also be having some physical doubt sessions. Gradually, we are starting the offline classes also, but initially with only doubt sessions and then eventually with the proper offline classes. So I would encourage you to pick up the doubts in the physical offline session when it happens. Otherwise, just send it to me on WhatsApp because I have another lecture coming up right now. Okay. I'll give you some hints on WhatsApp.
Okay, sir.
Okay.
Okay, okay.
Thank you so much.
Okay, bye.
Thank you, sir. Bye. Sir.